Hi, my name is Julian Hunt. I had to record this presentation because my wife's grandmother died, and during the presentation, I would be in her funeral. So I'm very sorry. I'll try to make it to the round table in the end of the conference. I am from IASA, the International Institute for Applied Systems Analysis, and I will present my work on seawater air conditioning and ammonia district cooling, a solution for warm coastal regions. This is a paper, this is presentation is in a paper in Energy, published in the beginning of the year, and ammonia refrigeration is used in industrial processes to distribute cold for different processes. However, is not yet implemented in district cooling. District cooling is very rare because of its efficiency and high costs. However, I propose ammonia for district cooling, particularly interesting with seawater air conditioning, and it's the first proposal for you to use ammonia as district cooling. At least I didn't find any other reference for this. Very quickly go through the potential for seawater air conditioning. You probably already mentioned seawater air conditioning. 1 meter cubic per second of seawater air conditioning is equivalent to 42 wind turbines, 136 football pitches, and a large hydropower plant. So with a little water flow extracted from the deep sea, you can provide huge amounts of cooling for particularly coastal regions and islands. I have already mapped the cost for SWAC around the world. The highest potential is in Pacific islands, Caribbean islands, so small islands. You also have some potential on the coasts, so huge potential, low costs. Comparing the costs at different islands, different cities, large cities, you have Honolulu, Havana, San Juan, Dominican Republic, Saint Pierre, Mali, Ilhéus, em Brazil, Puerto Escondido, Recife, Porto Moresby, Porto Gentil, Salvador, Abidjan, and San Diego. One of the aspects which I will try to focus in this participation in this conference is the need to increase cooling demand, because the higher the cooling demand, the higher the pipes. The higher the pipes, if you increase the diameter, if you double the diameter, you increase the flowing area, the area for the seawater to flow in 4 times. You reduce the friction, which it would increase the flow of water even more, 5 times, could be even 6 times higher. You would reduce the losses for the environment in your pipeline, because the higher the diameter, the lower is the ratio between the area and the volume that you transport. And so it has a significant drop in costs, particularly in the offshore pipeline. The district cooling cost doesn't change so much, but it has a huge impact on the cost of the offshore pipeline. So this is the main focus on my participation. And how are you going to distribute this cold? Ammonia is one option. Ammonia is how the system works. You extract water from the deep sea. This cold water is used to condense ammonia. The condensed ammonia is pumped to your district cooling system, distribution system. The ammonia vaporizes, and then it's automatically directed to the condenser because the pressure is lower, so you don't need compressors, for example. It just flows to to the condenser because the pressure in the condenser reduces because you condense the ammonia. So the water, the seawater arrives at 5 degrees. It can leave at 16, for example. The liquid ammonia arrives at 9 degrees, 9 to 18, depending on your system. You can have higher pressure that provides, so you have different systems. One that operates at 9, one that operates at 15, the other one operates at 18, for example. And then the ammonia gas comes back at a similar temperature. The pressure of ammonia, so for example, 6 bar, the pressures or the temperature of condensation of ammonia is 10 degrees. 8 bars, you have something like 18 degrees. So the pressure of your system will vary from 6 to 8 bars in order to provide this temperature, in order to transport the cold from thwack at from 10 to 18 degrees. It could be lower also, and the pressure will be lower. Comparing with steam, steam is the most used element to distribute heating in a district heating system. Ammonia I'm proposing here for district cooling. So the latent heat of ammonia is smaller, 60% smaller. The liquid density, it's smaller also. However, the gas density is higher, is 50% higher than steam, which is great because the more challenging is to transport the gas because of the lower density. So this is great. If you combine then the latent heat with this gas density, you have that the latent heat per volume is similar to steam, and so you can use ammonia similarly to steam. The problem is to distribute the cold. So when you are distributing heat, the steam is at 120 degrees, then you can have 20 degrees. In order to heat up from 20 degrees, you have a huge temperature difference. With ammonia, the temperature difference is very small, only 10 degrees. And then this is the main challenge, is to cool down a building. You have very small temperature difference. You can use this with several systems. For example, uh, with air, you can blow cold air into a room. Have several solutions for this. The cold air goes down, which this is appropriate in order to cool down a building. Ammonia and water. So comparing, for example, the use of ammonia. Ammonia uses latent heat. Water uses sensible heat. So then you increase also the temperature difference if you use ammonia, which makes your uh, refrigeration more efficient, refrigeration system more efficient. Comparing fresh water, so conventional swag with ammonia, you have that the heat transported by weight, it's 10 times higher. So you have to pump less, significantly less ammonia than water. The temperature difference in sensible heat, you have 20 degrees Celsius as the maximum. Of course, you might only use 5 to 8 sensible uh, sensible heat of water. Ammonia, of course, you use the latent heat. Customer investment requirements: water is high, ammonia is low because of the pipes are significantly smaller, so the cost of the system is significantly lower. District cooling capital cost is low. Pumping cost is low because you need to pump much less ammonia. District cooling distance, this is designed for long distances, so you can reach 10 kilometers away from the coast, maybe even 30 kilometers depending on the volume of your cooling demand. So you can reach much further into the coast or into an island to provide cooling. You have cooling demand potential is high, so the idea is to, when you have high cooling demand, you want to distribute this cooling demand, high cooling demand, you use ammonia. Risk of accidents I is high, but it can explode ammonia. It's toxic, but you have, for example, methane, natural gas pipelines distributing natural gas in houses nowadays. It explodes sometimes, but not very often, and you can take measures in order to minimize these risks. You can store seawater in freshwater tanks. Also, you can store for ammonia systems. You can store thermal energy close to the customer. With water is not so practical. With ammonia is practical, which makes ammonia a better system. This system, for example, proposes several ammonia district cooling systems, one with 6 bar, 7 bar, 8 bar, and then you use the final potential for water cooling, for example, for green farms, vertical farming, other purposes. For example, if you can store water in a tank, fresh water in the tank, this would be the volume. It stores the same amount of water as 18 Tesla semis, and the volume of the tank of ammonia is significantly smaller. You can store the same amount of energy with a very small ammonia tank that you can put close to the final customer to improve the efficiency of your distribution system. Of course, you have to always be storing the same amount of liquid, because if not, the pressure of your system will increase. So what you can do is that you can have, for example, when your demand is low for heating, you increase your tank close to the SWAC plant, and then you transport the liquids to the customer when the demand for cooling is high. You use more ammonia, and then most of the distribution system is used to transport the vapor into the SWAC plant, and then the SWAC plant has all the liquid ammonia stored. As I mentioned, ammonia is toxic, so there's a problem there, but with technology and very clever engineering, you can minimize the risks. Another interesting point is that ammonia is going to become one of the future fuels in the future, so we'll have a lot of experience using ammonia as a fuel, for example, in a future hydrogen economy. The conclusion is that SWAC is suitable source of energy with huge potential in tropical islands and coastal areas. SWAC is a valuable alternative to 100% renewable generation islands. A 17 meters cubic per second seawater flow can provide 1 kilowatts, 1 gigawatt of thermal energy of cooling load. The higher the cooling demand, the lower the cost for cooling with SWAC. Ammonia district cooling is a missing link for SWAC district cooling solutions. Ammonia is a better alternative for cooling thermal energy transportation than steam. And the future hydrogen economy will make ammonia a more acceptable and will reduce the risks of using ammonia. Thanks so much. I won't be able to answer your questions maybe, so please send me an email to hunt@iasa.ac.at. I'll try to make it to this presentation. Thank you. Have a nice conference. See you in the round table. Bye bye.